Hi, my name is Allison Vermock, and this is my Lab 3 presentation titled Black Holes. The goal of this lab was to estimate the mass of a black hole by observing the motion of a star orbiting around it. This lab will be conducted using code in Python, and the mass of the black hole will be estimated from numerous net force values and Newton's second law. The main concepts of this lab are Newton's second law, specifically how it relates to parallel and perpendicular motion, and Newton's law of gravitation. From Newton's second law, we can see that it defines the net force as the change in momentum over the change in time, and it can also be assumed that the resultant vector of net force is equal to the sum of its parallel and perpendicular F-net components. We can also see that dp dt is equal to dp dt parallel plus dp dt perpendicular. In this lab, the fundamental interaction is the gravitational force between our system, the star, and its surroundings, the black hole. We will assume that this is the only force or fundamental interaction acting on our system. Since this lab is coding heavy, I broke the model construction explanation into 3 sections: initialization, calculation loop, and graphing. In the initialization phase, I inputted my Georgia Tech email address to generate a unique trajectory. I also entered in the gravitational constant value, the mass of the star being 2 times 10 to the 30th power kilograms, and the time interval of 24 hours converted into seconds. Next, in the calculation loop, I used the momentum principle to define the initial and final momentums, being mass times its velocity. Then, using the notion that the change in anything is the final value subtracted from its initial value, I calculated the change in velocity and the change in momentum. Next, I defined dp dt as being the change in momentum divided by the change in time. Finally, using Newton's second law, I deduced that F-net is equal to dp dt by isolating F-net in the equation and also looking at the line of code above. In the second part of the calculation loop, I solved for p hat as being the vector divided by the magnitude, since it is known that a vector is comprised of direction and magnitude. So moving down the code, I figured that the change in the perpendicular momentum would be the change in the momentum minus the change in the parallel momentum via the equation to the left and the one I spoke about in the first slide. Next, here the magnitude of the gravitational force exerted on the star by the black hole is equivalent to the magnitude of the perpendicular net force value. And finally, I used Newton's law of gravitation to isolate the mass of the black hole variable and called it mbh in this code. Finally, in the last section of the model construction, I graphed the forces by finding an arrow scale that would be visible and not too large for the scale of the model. I took 1/3 of the average distance between the star and the black hole and divided it by an F-net value. My arrow scale came out to be 1.3 times 10 to the negative 17th. So after running the code, these were my results. The average mass of the black hole was 1.86 times 10 to the 34th power, and it fluctuated between 1.8 and 1.9 times 10 to the 34th power kilograms. This shows us that the model is flawed overall, since the mass does fluctuate. And in the model, the F-net vector in orange faces towards the black hole, the F-net parallel vector in magenta goes in the direction of the motion, and the F-net perpendicular vector in cyan points towards the center of the kissing circle. As you can see, the arrows are the largest when the star is closest to the black hole, and the smallest when it is furthest away. This proves that the model is correct in visually representing that the gravitational force, in our case the F-net value, increases when the distance is minimal. But in reality, the black hole would not be the only gravitational force in space. So finally, let's discuss that mathematically, the values for the net force components and the rate of change components are mathematically equivalent, since both can be broken down into the following components of dp dt. However, it is important to understand that conceptually they are different because the net force is the cause of the motion change, and the change in momentum is the observed effect of the net force. So to answer the what if question, gravitational force is impacted by distance and mass, and if the orbital motion of a star does not change, then you cannot tell the difference since it is assumed that the star's mass would remain the same also. This concludes this lab presentation. Thank you for watching.